Hello, everybody. Welcome back to Learning as a Hobby. In this video, I'm going to be doing the exercises in this book, Differential Equations with Applications and Historical Notes by George Simmons. I'm going to do some of the exercises from section 1.1 and 1.2. So I'll just jump right into it. I went over the lecture note. I keep saying lecture notes. They're not lecture notes. I went over my summary. Maybe that's a better word to use for it. I went over my summary for the section 1.1 and 1.2 in that book. A few minutes ago, I posted that to the channel, and now I just want to go over the exercises that I chose to do. Like I said, I didn't do all of them because there's too many to do on a single video, but so let me just bring that up. All right, so here's the exercise that I chose to do. I just picked some ones that looked interesting, and I just went through those. I skipped over question number one because question number one, there was a bunch of parts to it, and it was just verifying that that certain functions were solutions of certain differential equations. So I started with question number two, and I did those four parts. There was obviously a bunch of parts to it, but I did part C, I, O, and Q. Then I did part F in question three. I did part D and E in question four, and then I did question 5, 6, and 8. All right, so I guess I'll just go through them here. All right, let me move this up a little. Okay, so question two says the instructions are find the general solutions of each of the following ODEs. If you remember, ODE means that's for ordinary differential equation. So the first one, part C, they want us to find the general solution to this equation. Y prime equals x times e to the x squared. This problem is very straightforward. It's just a substitution. So you take the integral of both sides. The left-hand side is just y, and the right-hand side is the integral of x e to the x squared dx plus c. This is a substitution. Where's my marker? So here you just substitute x squared in for the variable of integration. So in other words, let me do this in a different color just to make it stand out against what I have already written. So in other words, you let u equal u equal x squared. And then the differential is 2x dx, which gives you the 1/2 du equals x dx. And that gives you this integral here. And then you just anti-differentiate, and you get 1/2 e to the x squared plus c. Okay, the plus c gives you the gives you the general solution, right? All antiderivatives that differ by a constant. Okay, that's part C. Part I, they want us to solve this differential equation, y prime equals y minus 1. This one is separable, so you just divide both sides by y minus 1 and divide both sides by x, and you get this differential equation here. Then you integrate both sides. Y prime, remember, is dy dx. So you just take the integral of both sides with respect to x. On the left-hand side, you have to make a substitution in order to integrate. Let me just scroll down. On the left-hand side, you let you let y equal u plus 1. The differential then is dy equals du, and then you plug it in. You get u plus 1 over u du on the left-hand side. The right-hand side is just a straightforward integral. The integral of 1 over x dx is the natural log of x, absolute value of x plus c. In this book, should make a note. This just reminded me. I should make a note about this. In the Simmons book, he says this stands for the natural log. This is log base e. So in other words, he's going to call this with the name log, but you might be also familiar with the notation ln of x. I understand this choice here. I understand this choice. It maybe makes more sense conceptually than this notation, but I find that this notation and maybe it's just my experience. I don't know. I find this notation to be more prevalent for the natural log. But like I said, there are reasons why you would want to call it with just log as opposed to having this strange looking notation for it. But it's just for the rest of this book, just be aware if you see log, this doesn't stand for the common log. It stands for the natural log. It's log base E rather than base 10. It's just a idiosyncrasy with this book. So, okay, so that's the integral on the right-hand side. And then you can easily integrate the left-hand side now that we've made the substitution. U plus 1 over u is the same thing as 1 plus 1 over u, and the antiderivative of that would be u plus the natural log of absolute value of u. That equals the right-hand side. And then just turn u back into what it represents in terms of x. Sorry, in terms of y, rather. And then you could raise both sides to take both sides as powers of base e, and everything simplifies to give you this equation here. So you get this equation here. And then you could divide both sides by the arbitrary constant c. And this is also constant. So you could take both of these things, incorporate both of them into the arbitrary constant here. And writing it that way lets you solve for x in terms of y. Right, so that's the solution to that differential equation. For part O, we want to solve this differential equation here. And again, this one is also separable. So you bring the y tan x over to the right-hand side, which gives you negative tan x on the, negative y tan x on the right-hand side, then divide by y, and you get this integral equation here. The left-hand side is an easy integral. That's ln, the natural log of y, absolute value of y. And on the right-hand side, again, that integral is just a substitution. Tan x is sine x over cosine x, so let u equal cosine x, and then you can find the direct antiderivative for that, which is ln of absolute value cosine x plus c. And that gives you the solution. Then you take both sides as powers of base e and simplify, and you get this solution curve here, y equals c times cosine x. Okay, so basically these are just Calc 1 problems. Part Q, they want us to solve this differential equation here, 1 plus x squared dy plus 1 plus y squared dx equals 0. Again, this one is separable, so actually I didn't even separate it. I just divided through by 1 plus x squared y times 1 plus y squared, and then you get this equation here, and then you just integrate both of those things. 1 over the integral of 1 over 1 plus y squared dy is just arctangent of y. Same thing for the other one, only it's arctangent of x equals c. And then to solve for one of the variables, you can take the arctangent of, you can take the tangent of both sides and use the sum formula for tangent. So the left-hand side then becomes y plus x over 1 minus xy equals the constant c. And then you solve that rational equation for y, which gives you, when you do that, gives you this function of x. So y is c minus x over 1 plus cx. So that's the general solution curve. In case you've forgotten, maybe I should write if you remember the sum formula for tangent, looks like this. So that's what I use to simplify the equation above. So I think that was all the parts to question number 2. Yep. Okay. Question number 3. I think I did one part, which was letter F. For each of the following differential equations. So there was multiple parts to this. I only did one part though. For each of the following differential equations, find the particular solution that satisfies the initial conditions. And I think I chose this one because it's a partial fraction decomposition problem. So we want to solve this differential equation when x is 0 and y equals 1. And then you just go through your process of doing your partial fraction decomposition. And when you do that, you end up with this on the right-hand side. Okay, and that gives you 3 easy functions to integrate. Okay, which I do down here. The integral of dy dx is just integral dy, which the antiderivative of is y. And then on the right-hand side, the first integral gives you a logarithm. The second integral also gives you a logarithm after you make a u substitution. And the third integral gives you an arctangent plus your arbitrary constant. And then you plug in the initial values. So you plug in, what were they? We wanted x equals 0 and y equals 1. So if you plug in those initial values, where did I do that? Down here. Okay, so in that line, I plugged in 0 in for x and 1 in for y. And that allows you to solve for the arbitrary constant c, which gives you a value of 1 when you do that. All right. And then when you plug in that value for c, you get this equation. And then you could, if you want to, you don't have to, but if you want to simplify the logarithms, you can use some of the properties of logs to simplify it to the one I have in the box. If you remember, sums of logarithms are the same as logarithms of the products, and so on and so on. There's a bunch of properties of logarithms. All right. For question number 4, for each of the following differential equations, find the integral curve that passes through the given point. Okay, so again, we have this differential equation that we need to solve, and the initial value or the point that we want the integral curve to pass through is the point pi over 12 comma pi over 8. All right, and here, if you notice, this is an exact differential if you factor out the dx. And if you look at the function that we have over here, this part, if you notice, is the derivative of this, and sorry, not of the, without the 2. And let me change the color. This, this part here, the 2 sine 2y is the derivative of cosine, the negative 2 sine 2y is the derivative of cosine 2y. So in other words, we just apply, it looks like we just applied the product rule, right? So you can rewrite this as the differential of that product of functions. That's equal to 0 because the right-hand side is equal to 0. And if you integrate that, the left-hand side, you just get sine 3x cosine 2y equals an arbitrary constant. And then you plug in your values. Sine of 3 times pi over 12 is the same thing as sine of pi over 4, which is 1 over radical 2. Cosine of 2 pi over 8 is the same thing as cosine of pi over 4, which also is 1 over radical 2. 1 over radical 2 times 1 over radical 2 is 1/2. So that's your value for c. And then if you just multiply, you plug that value in for c and then multiply through by 2, you get this solution, this particular solution that I have written down here. 2 sine 3x cosine 2y is equal to 1. Okay, what's next? Part E. Oh, so same problem. What number problem was this again? Number 4. So part E for number 4. Oh, I wanted to do this because it was an integration by parts. So we want to solve this differential equation. Y prime equals e to the x cosine x, and the initial point is 0, 0. All right, so the left-hand side, you integrate, you get y. Right-hand side, you have to use integration by parts. Actually, you have to do it twice. This is one of those annoying integrals where you have to use integration by parts twice, and then use the fact that the original integral shows up in the when you're anti-differentiating, and then you can use that to solve for the general antiderivative. Or sorry, the indefinite integral. So here I'm doing my integration by parts the first time. You get this Let me get my marker. So here I'm doing integration by parts the first time, and that gives you this over here. And then to do the second integral, I integrate by parts again, and that gives me this. When I simplify everything, I'm calling I the actual original integral, and you could add I to both sides. That gives you 2I equals e to the x times sine x plus cosine x, and then divide by 1/2 and add your arbitrary constant, and that gives you the indefinite integral. And then we can plug in our values. They wanted x equals 0, y equals 0, and that'll let us solve for c. And when you do that, as you can see over here, you get that c has to be negative 1/2, and then you just plug it into the general solution, and you get this particular solution. All right, I hope I'm not going too fast. Okay, and then number 5, they want us to show that this function here, y equals e to the x squared times integral from 0 to x e to the negative t squared dt is a solution of this differential equation. So all we have to do is just differentiate that function. You have to, in order to do that, you have to use fundamental theorem of calculus part. Well, different books number them the parts differently, but use the fundamental theorem of calculus. And when you do that, you use you have to differentiate by using the product rule, and you get this derivative here. And notice that these actually cancel to give you 1. And notice that this is equal to 2x times y plus 1, which shows that it satisfies the differential equation. Right? That's all you have to do to show that something satisfies the equation, is just show that when you plug it into the equation, you get a identity. All right. Okay, question number 6 says, for the differential equation, y double prime minus 5y prime plus 6y equals 0, carry out the detailed calculations needed to verify the assertions in the text that y equals e to the 2x and y equals e to the 3x are both solutions. So in other words, this was an example I did in the text. I actually didn't do it in my show it in my notes because he does it he asks you to do it in the exercises here. So the first one here is when I let y equal e to the 2x. When you plug that in to the differential equation, you get that, and notice 4 minus 10 plus 6 gives you 0. And then when you plug in y equals e to the 3x into the differential equation, you get this function here, and notice 9 minus 15 plus 6 is 0. So the equation is satisfied with both of those solutions. All right, for part B of that problem, which was, what number was that again? Number 6. They want us to show that y equals c1 e to the 2x plus c2 e to the 3x is a solution for every choice of the constants c1 and c2. In other words, they want you to show that the two solutions that we found above, if you take a linear combination of them, you still get you get the general solution. So all you do is, again, you just plug that function into the differential equation and show that it works. So here, when you do that, again, you end up with 0 plus 0, which is 0. Right? So you just, do the second derivatives and the first derivatives and everything, and just combine everything. Right, and then the last problem was this one, number 8. For what values of the constant m will y equal e to the mx be a solution of the differential equation? This one is third order, because notice that the highest order derivative that occurs is the third one, right? Third derivative. This is second derivative, first derivative, 0th order derivative. Right, so we want to figure out what value of the constant m in y equals e to the mx will solve that differential equation. And then they want us to use the ideas in problem 6 to find a solution containing 3 arbitrary constants, c1, c2, c3. So what we're going to end up doing is we'll see that when we go through the problem, you'll see that we get 3 different solutions, and then we'll just take a linear combination of them. All right, so if you plug y equals e to the mx into the differential equation and simplify, you get this this equation here, and e to the mx is never 0, so you can divide out by it, and you get this. So I just realized there's a typo here. This should be m cubed. All right, so you get this third degree polynomial equation. If you notice this equation, you can solve by just inspection. If you look at the coefficients, let me change the color of my marker here. If you look at the coefficients, 2 plus 1 minus 5 plus 2 is 0. So that means that m equals 1 is a root of that polynomial, or in other words, it's a solution to that equation. And we can use that fact and synthetic division to figure out what the other quadratic factor is. So here I'm using synthetic division. Right, so we have the factor of m minus 1. This is the quadratic factor, which factors into 2m minus 1 times m plus 2. And if you set those equal to 0 and solve for the roots, you find that the roots are m equals 1, m equals 1/2, m equals minus 2. So you take those as factors of the power in e to the mx. So we have these three particular solutions, and then you just take the linear combination of them, and that will be the general solution to that third order differential equation. Okay, and that's basically all the problems that I did in this section. It was a relatively, section 1.1 and 1.2 are relatively short. And there was only 8 problems for those sections. And like I said, I still didn't do all of them because some of them are very straightforward, like, just asking you to verify that certain functions are solutions to differential equations and so on. So I just did the ones that I found the most interesting. And I'll continue with this I don't know when I'll post the next video. It should be soon though, because the next video I want to do is the classical mechanics notes. I wanted to do that next, and I have to work on Schifrin's exercises for section 1.2. So let me just stop the screen share for a second. All right, so again, I hate to be annoying, but if you do like this content, please like and subscribe. It helps the channel grow. And let me know what you think in the comments, or if you have any questions or anything. And I'll see you guys in the next video.